We are continuing our discussion on Chapter 3, Lesson 1, and looking at applications of exponential functions. You should have already read the bottom of page 161 through 165 in your textbook, and what we have on the next page of your notes is a summary of this information. One application of exponential functions is compound interest. Okay, we have compound interest that's compounded a specific number of times versus compound interest that's compounded continuously. And we have two separate formulas for these situations. So the compound interest formula is as given. A equals P times the quantity, 1 plus R divided by N, all raised to the NT power. T represents the number of years. A is your initial balance. Your balance in the end. P is your initial balance. R is your annual interest rate, and we always express R as a decimal. Okay, and this is true when we are compounding N times a year. Now we're going to use this formula, and I want you to turn the page and look at problem number 1. It says, Mrs. Salzman invested $2,000 into an educational account for her daughter when she was an infant. The account has a 5% interest rate. If Mrs. Salzman does not make any other deposits or withdrawals, what will the account balance be after 18 years if the interest is compounded? And we're going to check it if it's compounded quarterly, monthly, or daily. Now, we need to identify the information that we are given. Okay, Mrs. Salzman invested $2,000. Okay, the amount that she invested is our principal balance. It's the initial amount. The account has a 5% interest rate. Now, if it has a 5% interest rate, as a decimal, we move it to the left 2 places. That is going to be 0.05, okay, because 5% is 5/100ths. Okay, now the other thing we want to figure out is what is the account balance after 18 years. This represents our time T. Now in letter A, we want to know what the account balance is if it is compounded quarterly. Quarterly is 4 times in a year, so in letter A, N is equal to 4. So using our formula, A equals, that's the account balance we're trying to find. P is our principal. The initial investment was $2,000. We have 1 plus R divided by N. R is 0.05 divided by N, the number of times it was compounded, that is 4. And then my power is N times T. So in this case, that's 4 times 18. Now, this is really a lesson on how to use your calculator. We're going to plug this into your calculator, but we are going to use order of operations. Now, I do need to know what 4 times 18 is. So I'm going to take 4 times 18 on my calculator, and I get 72. I'm going to write that down so I have that information. Okay. Now, I always start with what is inside parentheses, so I'm going to take 0.05, divide that by 4, and I get 0.0125, and I'm going to add 1 to that. So I just completed what was inside parentheses. Next is the exponent, so I'm going to raise this value to the 72nd power. So on my calculator, I'm going to push the caret button to the 72nd power, and I get a long decimal. Now I'm going to multiply this value by 2,000. The answer is my account balance. Okay, this is money, so this represents dollars and cents, so I will always round to the nearest hundredths. So this is 4,000 $891.84. Okay, next I want to calculate what the account balance would be if interest was compounded monthly. Now think about how many months are in a year. There are 12. So that means n, the number of times it's compounded, would be 12. Once again, I'm going to plug this information into my formula. My account balance is equal to the principal, which is my initial investment at $2,000. Okay, times the quantity 1 plus my rate is still 5% interest rate, 0.05, all divided by n, which is 12. My power, n times t, would be 12 times 18. Once again, it's helpful to me when I plug this in my calculator to know what 12 times 18 is. So I'm going to go ahead and calculate 12 times 18. I get 216. I'm going to move this over to the right. Again, the rest I'm going to plug into my calculator. So I'm going to take 0.05 divided by 12 and add 1 to that answer. Okay, this is the value when I calculate what's inside parentheses. And I'm going to take this number to the 202nd power. So without erasing, just hit your power button, 216. And then multiply this by 2,000. Do not round until the very end. So my account balance after 18 years compounded quarterly is $4,910.02. Next, I'm going to calculate to see what the account balance would be if the interest was compounded daily. Now, within daily, how many days are in a year? So n would equal 365. So once again, I'm going to plug the information into the formula. So A equals, my principal is 2,000 times 1 plus R is 0.05, all divided by n, which is 365. Okay, and then my power, n is 365 times 18. Okay. To help the calculations go easier, I'm going to take 365 times 18. 365 times 18 is 6,570. And now I'm going to calculate what's in the formula. In parentheses, division comes first, so 0.05 divided by 365. I'm going to add 1 to that. That takes care of what's in parentheses. Now I'm going to raise this to the power of 6,570. Then multiply that by the principal 2,000. Okay, the final account balance would be $4,918.90. As you can see, the more we compound the interest, the higher the account balance. Now, this is the formula that you can use when you compound interest a specific number of times a year. So this works if you are buying a car and you're trying to calculate in the interest rate, or the interest rate for the loan for a car. And it works for many different things that you are trying to buy, and you have to actually purchase a loan and pay interest on that. Now, on certain occasions, interest may be compounded continuously. That means all the time. When we compound continuously, we use A equals P e to the RT power. So notice we are using the natural base. A is our account balance, P is the principal, R is the interest rate, and again the interest rate has to be used as a decimal, and T is the time in years. Now we're going to use this formula to complete problem number 2. In problem number 2, Mrs. Salisman found an account that will pay the 5% interest compounded continuously on her $2,000 educational investment? What will be her account balance after 18 years? Okay. So because we are compounding continuously, we're going to use the formula A equals P E to the RT power. Okay. Now, my principal, again, is the initial investment at $2,000 times E. My interest rate is 5%. As a decimal, that's 0.05. And T is the time in years, and we are compounding this continuously for 18 years. Now, when we solve this equation using the formula, again, we have to follow order of operations, so we know that exponents come first. So once again, knowing the 0.05 times 18 is going to be helpful to me, so I'm going to go ahead and calculate that. I have 0.05 times 18, and I get 9. I'm sorry, I think I miscalculated that. How about 0.05 times 18, and I get 0.9. Okay, so when I calculate, exponents come first, so I actually have to calculate e to the 0.9 power, and then I multiply that by 2,000. And we get $4,919.21. Okay, I would like for you to try number 3, letter A and B, and then check your answer with the key that is posted on Canvas. Now pause the video while you try those. I'm going to go ahead and look at the last example, which is modeling using exponential growth and decay. Okay, a state's population is declining at a rate of 2.6%. The state currently has a population of approximately 11 million people. If the population continues to decline at this rate, predict the population of the state in 15 years using each model. A is annually and B is continuously. Now, when we are not dealing with compound interest, okay, we do have specific formulas for exponential growth or decay. Okay, for exponential growth or decay, we use n equals n sub 0 times the quantity 1 plus r to the t power. R is your rate as a decimal. N is your final amount, and n sub 0 is your initial amount. T is time. Now your rate, when we're dealing with a growth, your rate is going to be positive. And when we are dealing with a decay, your rate is going to be negative. Now for continuous exponential growth or decay, okay, again we have our exponent with the natural base e, but everything else stays the same. N sub 0 is the initial amount, n is the final amount. Instead of r being your rate, we use k as your rate, again written as a decimal. And if it's growth, k will be positive, and if it's decay, it will be negative. Okay, so for letter A, okay, first of all, we are calculating this annually. Annually means one time a year. Okay, so a state's population is declining at a rate of 2.6%. Okay, so if it is declining at a rate of 2.6%, then our rate has to be negative. So I'm going to write down declining. So know that this is decay. So our rate as a decimal, move the decimal place left 2 spaces, is 0.026. Okay, there's approximately 11 million people. So this is our initial amount. spell initial correctly. Okay, and they want to know if the population continues to decline at this rate, predict the population of the state in 15 years. Okay, so I know that t is equal to 15. Okay, because our rate is declining, our rate has to be negative. And then our initial amount, n sub 0, is 11 million. Okay, so using our formula, n is equal to, my initial amount is 11 million. And we have 1, but instead of plus r, since r is negative, we go minus 0.026 to the t power. T is the time in years. This will be after 15 years. Okay, to calculate this, I complete what is inside parentheses first. So I'm going to take 1 minus 0.026, and then I'm going to raise that to the 15th power. Multiply that by 11 million. And that means I have a population of about a little less than 7.5 million. Now notice there's a decimal. Okay, we typically say you can't have a half a person, so we would round that up. So in 15 years, the population will have declined from 11 million people to 7,409,298 people. Now we're going to model this also if we have a continuous rate as well, continuous exponential decay. So for continuous exponential decay, we have n equals n sub 0 e to the kt power. Again, k is our rate, so k is equal to negative 0.026. T is our time is still 15 years, and n sub 0, our initial population, is 11 million. So we're going to plug that into the formula and see what our outcome would be if we have continuous exponential decay. So n is equal to 11 million. E, kt power, so I have negative 0.026 times 15. Again, I'm going to multiply the exponent first. It's going to make the calculations easier. So negative 0.026 multiply that by 15. And check. So we have negative 0.026 times 15. We get negative 0.39. Okay, so I have e to the negative 0.39 power. And I'm going to multiply that by 11 million. And we get 7,447,626. So when we have continuous exponential decay, we will have a few more people remaining after 15 years compared to when we compounded it just annually. Okay, now I'm going to have you try a few problems from the textbook, so check the Canvas page to see what your homework assignment is, and make sure you make a list of any questions that you might have. Good luck.